Peace.
You can guess what band shirt I'm wearing. I'll give you $1. Oh, shoot. I thought it was Pink Floyd.
Anyway, gambling. Well, you gambled, I didn't gamble. I had nothing to lose.
I thought I was wearing something wrong.
I'm surprised.
That's 1,733. 0.
No, I think I had one for the review session last semester. You remember what I'm talking about? You had too much alcohol.
Oh, yeah.
That was funny.
What did I do?
You kept saying that you were someone on the work or something. I was like, you have too much alcohol. And my phone. It's a great start.
I've been like, I don't know, 80% of my life without one of those things, so.
I usually survive. I'm usually this week to coordinate going to work out this weekend. So.
Go to some place and try to bring people ahead of time where you're gonna meet them and like. Just have maps and stuff. It's crazy.
It's a lot harder to do that too. Half the people that are meeting don't really care to have plans. I football went to it's a national market day.
Okay.
So I'm debating how much other stuff I should wear.
Wasn't that spectrum? Are these automatically next to each other? Are these three stage two? Is that how they're written?
No, not necessarily, because remember the number of items can shift them. And then there's a like that on there, and then they shift it.
Okay, so if we just have the depth and nothing else.
From the numbers to stage 3. So you have 2 possibilities, but.
Some of those. I wonder why.
This one doesn't give me an option. They're one.
I'm starting to get better at it, Nate.
What?
I'm starting to get better at this.
Same.
It's like, no.
Kind of confused on what we viewed yesterday.
Yeah, there was
just like,
just really hard.
just talk, yeah.
It's just, it's like.
We'll understand it for sure.
You
But,
think so?
Yeah,
I certainly.
it helps when he goes over it.
It does.
It's so easy.
Like after I watched the videos again yesterday,
How many,
it actually was
Yeah. The problem with me is I have a
If you have 3 points, it's one of those.
microbiome test on Monday. So I have to like, over the weekend, focus on that. And then right after that, I'll shift all my attention. I mean, I'll still review.
You know all the radical reactions. You do.
I
Alright.
reviewed yesterday. So I have those down.
I need to get on those.
Yeah.
Just one peek aside.
You complaining about?
No.
I was complaining. Well,
She was
not
complaining.
complaining. I was asking if they knew the radical reaction. Like all the mechanisms. I know what they do, and I know some of it, but I need to. I've been too focused on this still.
Oh, it makes it, I need to create the mechanism really hard.
Oh, I know.
Make sure,
I
like,
emailed
every arrow went exactly where it did, and all the resonance structures were drawn.
Yeah,
And
no.
those big points, he said.
Please do that.
Yeah. He gave me a sarcastic remark today.
You went to his office hours?
No, I emailed him.
Oh, I got you. What'd
Here,
you
I'll
say?
show you.
Yeah, I need to see this.
Yeah.
I forgot about the 3 steps. The last one's easy though.
I was hoping it was like a short country. She's like, no, it's all 3 of them.
The last one's easy though, because it's just like you take a parent.
Your response is funny. I tried to pawn him off a goat yesterday, but he didn't want it.
I told him just to drop him off at Nate's house.
They would probably die within a day at Nate's house.
I didn't take care of them. Something my brother.
You think Trey?
Or my sister.
I don't know.
Yeah,
Who's more responsible, Avery or Trey?
This first
I'm out. I mean, probably, but it's close.
That's bad. Have you ever let Avery cut your hair?
Yeah, she did a good job.
Yeah?
Yeah, I mean, she only has, so the first time she cut my hair, she has only cut girls' hair.
Oh, yeah.
So I was the first.
You were the first guy.
I was like, come on, hold it together, lock in, because it was like right before I was coming back. I was like,
You let her do that before you.
yeah, and I was just like, lock in,
Oh.
like do not mess up.
What if you would have done if she would have messed it up?
Oh my gosh, that would have been.
How do you have glitter in your hair? You have glitter in your hair. Oh. Yeah, there's glitter all in your hair.
I don't know.
You didn't shower after the club last night.
Yeah, apparently not.
It's turned red.
Where did you? I can see it. It like glistens sometimes. Maybe you just dusted it out, but there was glitter in your hair.
I don't know. I don't care.
There was like 3 little specks that I saw in your hair.
I don't know.
Interesting. Bro, I was so mad at my mom because she's at that conference in Indy, and I asked her to bring my new running shoes because these hurt now because they're worn. And
Wait, do you not have running shoes up there?
these are what I run in.
Oh, the books.
Yeah, but they're worn down because I've had them for a while.
Yeah.
So I asked her to bring. I got new ones for Christmas, and I was like, "Can you bring those, please?" Because these have been hurting. My feet were literally bleeding after my last run. And I asked her, and she's like, "Yeah, I can do that." And I called her yesterday. I'm like, "Did you remember my running shoes?" No, she did not.
What other running? Do you have like books?
Well, I have another pair of Brooks here, but they're older than these. So basically, I'm screwed either way.
Why don't you just bring your time home?
I'm not going home until the 28th, which is the end of February.
Okay.
So I guess I'll just have to thug it out with these. Also, yesterday at practice, we scrimmaged the football team.
Did you really?
Yeah.
Oh, that good.
We almost beat them. No, I'm not kidding. We played to 15, won by 2, and we were up 14-13. And we ended up playing to 27 because we kept going back and forth, and they ended up winning because they dunked it. Yeah.
You're okay.
And we played another game and we lost that one.
Honestly, the fact that you kept it close is.
We were literally winning. Like, we only had to score 1 point and we would have won. And then we ended up playing until 27 instead of 15. 1s and 2s, obviously.
That's pretty good. How long did you guys just scrimmage in practice?
No, we actually do like drills and stuff.
No,
But
you guys do.
yeah. We have a coach.
All right, happy Friday, everyone.
Yeah, it's just fun.
Yay.
Yeah.
Grinder, review session Monday night, 7 o'clock, 3 questions in the room. And then exam get here to start at 8:15, so I can give you the full hour. As you can see, we're going through these problems sometimes. having that extra time to be able to go back and check things and not feel so rushed is important. So I'll give you guys as much time as I can to still demonstrate what you know. Okay, what do you think of the 5 problems I sent out yesterday? Tricky. Easy? No, those weren't easy. Those were difficult. So the point of this is if you can get through these 5 and feel pretty good about your process, the exam will be able to see in terms of the spectroscopy. Remember, we still have radical stuff and we still have everything from day 1 of organic 1 that you're responsible for. Nothing ever goes away in this class. So yeah, so that's all there. But if you got this down, the exam questions will be a step forward. So this is part of why I gave it, not just to torture you, but to really see and push yourselves to make sure that you got all of these steps. So we're going to go through these 5, or as many as we get through today, and see how we did, and I will post the key for this for you all when I get back to class. Also, I apologize, I didn't get through the homeworks that you turned in yesterday for grades, but I'll be looking at that tomorrow. So I'll be there then. For comments, I'm not making a whole lot since we went through in class, and then also I posted the key, I believe. Yeah, I did post the key on that one. So I'm just gonna make some general comments. Okay. But if you have questions, let me know. All right. So first one, let's go through this one, and I'm gonna go kind of quick on some of the pieces, and then a little more in detail on the things that are a little more confusing. All right. So mass spec there, we want to check out, try to find out their 9 cluster, which is most likely here. We look and try to figure out which of those peaks make sense. So this one does not make sense because you're not going to have an n+1 that's much bigger because the only way you have n+1 is through the isotope stuff. All right, so it's either this one or this one is our pair 9, which is either 108 or 107. Okay, we do have nitrogen in here, so you can take multiply either 108 or 107 by that, and then see how it comes out. Okay. If you got 1 nitrogen, then, or 3 nitrogens, or 5 nitrogens, then you know it has to be the 107. If not, it's the 107. Okay, so you can process elimination that if you're not sure about this one. It is actually 107, and there's 1 nitrogen. You can do this one. Okay, so it comes out to be C7H9N. And UU is equal to 7 minus 9 halves, which is 4.5, right? Plus 1/2 plus 1. 7 minus 4.5 is 2.5. Plus, people do this wrong all the time with nitrogen, by the way, so just double check. So doing step 1, 7 minus 4.5, 2.5 plus 1/2 is 3 plus 1 is 4. All right, so we're thinking benzene right off the bat, right? 4 units on saturation that we need to look for. Go.
Is there, I was doing math for this one yesterday, isn't there a way you can do that to get 3 units on saturation?
Nope, that's why I said do the maths
Okay.
properly, because they mess it up all the time. So like if you try to
That's what I did. Was
10, 5, 7 minus 5, yeah, so if you add these together and make 10 halves and 5,
You get 3.
yeah, but it's, remember, it's negative here.
Yeah.
So it's actually 8, which then gets you 3 plus 1 and 4. But people take these and add them together and then subtract.
So no.
Yeah, because that's not how it works. It's a negative 9 halves. All right, does that make sense to everyone? Okay, so we're looking for benzene. Also in the mass spec, I mean, there's these other things. We can look at fragmentation. You don't need to. If you want to go back when you get stuck places, sometimes it's a good place to do, but I would not say do anything significant other than to know that our pair 9 is large, which means we have a pretty stable molecule that's not going to break apart pretty easily. Okay, so that helps us as well. All right, so we look in the IR. We think we have benzene, so we want to see if we see that. We also have that nitrogen. All right, we got this guy over here, which looks weird to me. And like I said, the more of these things you look at, the more you kind of start seeing what things look normal and not normal. That looks pretty non-intense for an NH. Okay, it's in the right region, it's in the right appearance, but it could be an NH, it could not be an NH. So I'm going to have to look for additional information to see if I see that NH. So where would I see that NH if there was an NH? In the proton atomar is where that's going to come, right? So if I pull my proton atomar, I should see a 1H signal that's broader, because our OHs and NHs, remember, become broadened because of hydrogen bonding, and they don't split. nor do they split the things that they're next door to. Okay. So do I see a broad 1H singlet anywhere? Sorry, can't see that. Okay. I do not. Okay. We have triplet, doublet, doublet. So no, that's all got splitting. Singlet, singlet. But those are 3Hs. So we have no evidence of an NH in here. So what that tells me is that's hydrogen bonding to a nitrogen. It's lone pair that does not have any hydrogens on it. Does that make sense to you all? Okay. So I have a nitrogen that I have to deal with. And no hydrogens. Okay. All right. So we said benzene, we thought, right? So we look at our proton. We got peaks in the benzene region, 3 hydrogens. Okay. With 3 hydrogens would be tri-substituted benzene. Okay. So let's go to our carbon NMR and see what we see here. All right. Well, I only have 2 singlets in here for substitution. I also only have 5 carbons in this benzene region. I have 7 carbons total in my molecule. Here's 6, 7. I didn't say that on purpose. That's really unfortunate. All right. Anyway, so here's 2. I really didn't do that on purpose. You got 2 and 5. What is that telling you then? These have to be 2 methyl groups. Quartet 3H, quartet 3H. And we got 2 methyl groups in there. We can't have more carbons than there are in the formula. What gives? You have any ideas? It's not a benzene, but it's something very, 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 very close to benzene. All right.
The nitrogen, like the benzene instead of carbon.
Absolutely. So the nitrogen now is no hydrogens on the nitrogen, and we still possess this aromaticity of the ring that makes it especially stable after you replace that. Okay? You can't add carbons to the formula. It doesn't work that way, right? And then you get all kinds of hard stuff to try to make things fit if you try to make it fit. Okay? Benzene was the right first approximation, but then everything else after that tells you, yeah, it's like benzene, but it's not benzene. Okay? Does that make sense to you all? And why? Okay. So then our pieces become a little easier. We have our ring with the nitrogen in it, and then 2 methyl groups, and this has 2 positions of substitution, right? Because we have in our carbon NMR, we have 2 singlets and the 3 doublets for hydrogens on 3 of the carbons, no hydrogens on 2 of them. And then also in the proton NMR, we have 3 hydrogens, right, in the aromatic region. So if we substitute 2 of the positions, 1, 2, 3 would be left unsubstituted. Okay, so it's a di-substituted. This is called purity. So remember when we write PY for the SOCl2, this is purity. Okay, and it's unsubstituted. All right, you with me so far? Okay, so got our pieces. Life gets a lot easier after we get our pieces because now we just have to take the smaller pieces and make them into bigger pieces. Since these are going to be singlets, there's no hydrogens next door, which means we can't attach them to one another, which we already knew because we've done the molecule. Really, the only thing we can do is put them on the ring. Okay, so now we got to figure out the substitution pattern, just like we did with our normal benzenes. We use the splitting to figure that out. Okay, so we have 1H doublet, 1H doublet, 1H triplet. What are our possibilities for arrangements? Just like we did for the other one, we have this one. We have this one. Okay, if I put it over here, that's another one. This one. I have that one. That one. I'm going systematically through. I started with it right next door, and then I moved the other one around the range of all the possibilities. Then I move to the second position from the nitrogen and look at all the possibilities. I can't put the second one here. I recreate that one. So move to that position and then this position and then this position. So now I'm going to go third position. So if I put it here, I recreate. Put it here, recreate. Put it here, I recreate because this is the same thing as this one. Okay. So I've gotten to a place where I've run out of additional structures on this thing, right? So this did not recreate anything new. You can prove it to yourself by going to the next one and see, but it's the same thing as going to that position.
Is that one, this one underneath that, not the same as the one at the bottom right?
Which one? Sorry.
The one right underneath the one you scribbled out.
This one right here?
Yeah, is that not the same as the one on the bottom right?
See, so we have it in a 1,4 next to the nitrogen. This is in a 1,4 next to the nitrogen. Okay. All right, so that's the game we play. Those are our possible arrangements for our system, for our framework. And now we're going to say which of these matches the splitting pattern that we have. This would give us a doublet, triplet, doublet. This one gives us a singlet, doublet, doublet. This one gives us a singlet, doublet, doublet. This one gives us a doublet, triplet, doublet. This one gives us a singlet, doublet, doublet. This one gives us a singlet, singlet, singlet. Okay. So what do we have? We have doublet, doublet, triplet. So anything with singlets are out. Doublet, triplet, doublet, doublet, triplet, doublet. Okay. So I have those as potential possibilities. With me so far? And with this one, what do we have? Symmetry. So are these actually two different sites? No. So this would give rise to one 6-hydrogen peak, right, for our methyl, and this would be 1 2H doublet and 1 1H triplet. Okay, so we would not see that pattern there for this one. Does that make sense? So the only possibility we have left is this one. So we know that's our arrangement based on our splitting of our NMR, and then the only groups we have here add our amounts. And it should be singlets in that region. Everyone get that one right? That's tricky, right? It's tricky. And it's just the reason why I do that. I actually hate doing it in part of the way because then you guys say, oh, we can do whatever we want to benzene and just start doing crazy things. Most, 99% of the time when you think it's benzene, okay? But that's not universal. There are other things that can come in that region. So if benzene, which I put up there in the first place, that's what I went with, right? But if I start having all this evidence that says, that's not looking right, you don't brute force it and say, nah, that's okay. I'm sure it's just a typo or whatever you put in your mind to convince yourselves of something else. And I'm guilty of doing this. I think I said in my video, I told the story about the fumes. Did I say this in one of my videos or no?
Mm-hmm.
Yeah, so yeah, you have cumulative examination. You show up, you get a 3-hour exam on anything. And on the spectroscopy one, and I was guilty of this. I forced it to be what I wanted it to be. I'm like, oh yeah, I can see how I could possibly do this. And yeah, I know this isn't quite the same, but it's close enough. And this is fail, right? So I had get 5 out of 7 then after that one, right? So that was not fun. Anyways, yeah, tough stuff. Okay, any questions on that one? Good. Do number 2. Move on. Aspect, percent comp again, get a formula. Okay, so Carolina cluster looks like here, 11, 12, 13, 14, 15. No nitrogen, right? So it's going to be either 14 or 16 on this thing. Does that make sense? Is that right? 11, 12, 13, 14, 15. Yeah. So it's got to be 14 or 16, not 13 or 15. Okay. That isotope pattern looks normal. Yes, I'm liking to work 14. I'm going to go multiply it out, see if it all comes out right. Because we're good. We do have a significant base peak here. So 114 minus 85 is 29, 39, something like that. probably like an ethyl or something, but don't have to worry too much about it. Can't figure it out right off the bat, don't worry about it. So that's really all we're going to get from this. Okay. So we go ahead and do all that math, and we come up with C6H10O2. You use 6 minus 10 F's plus 0 halves plus 1. 6 minus 5 is 1 plus 1 is 2. So once again, triple bond, 2 double bonds, a double bond, and a ring or 2 rings. Okay, so I want to go to my R and see if I can figure out what those are pretty quickly. Push this up. What do I see? No triple bond, right? But I do have pumpkin peaks over here, and I actually have what looks to be 2 things there. So one at 1700 and one about 1650, it looks like, okay, which would suggest to me a carbonyl and an alkene for my 2 uses. Okay. Let's go kind of confirm that suspicion as well. How am I going to confirm that? Well, I can do it pretty easily in my carbon NMR. Okay, I have my carbonyl peak all the way up here, and then I have 2 peaks in the double bond region for the carbon-carbon double. All right, so I got pretty good confirmation that I do indeed have that. It looks like maybe here on the AIR that could potentially be an aldehyde. How do I figure that out? Okay, proton and carbon NMR. In the proton NMR, I have the singlet at just about 9. This is characteristic of the aldehyde. And then what's really characteristic here is my carbon NMR, because it comes between 190, 220, and it's a doublet, which means it's attached to 1 hydrogen. So that's the only way you're going to get that in that region. Is if that. Make sense to everyone? Yeah? So we go ahead and start writing some pieces that we have already. We know we have aldehyde, and we know we have a carbon-carbon double bond. Okay? And we don't really know much else here. We have some, looks like sp3 hybridized carbons. We may have sp2. Can't really tell from the IR. Sometimes it's clear, sometimes it's not, but we have, once again, better ways to find them. Okay? So we don't spend a lot of time in there. I spent more time explaining, but it should have been about 30 seconds on that, and then going and confirming, and then putting this away, and then really spending all my time on proton and carbon. Okay. Questions so far? Okay, so I work these things in conjunction with one another, whenever possible. Okay, so we already did this. This is our aldehyde that we've already confirmed. Okay, this was our carbon-carbon double bond, and we only have 1 peak in that region. Okay, which tells us it's a trisubstituted double bond, and we got the confirmation here. The thing that means no hydrogens, and then the double means 1 hydrogen. Okay, so not only do I have the aldehyde and the double bond, I know it has to look like that. Okay. All right, continuing on, 2H, and then I got a triplet in, triplet in my carbon NMR to correlate to the 2 hydrogen signal. Go ahead, Maggie.
Can you explain again how you got the substitution?
Yes, so in the carbon NMR, I have multiplicity on here. And remember, these aren't the actual multiplicity; they're all singlets, but that's what they would be if you're in them. So it's the n+1 rule for the number of hydrogens on the carbon. So singlet says n is 0, and then d is 1. So we have 1 hydrogen on that double bond, which means there's substitution of all of the positions. Okay. So far, so good. Okay. So next comes my CH2, which correlates to the triplet, and then 2 CH3s correlate to my 2 quartets in the carbon NMR. Okay. So I have CH2. I have CH3, and I have CH3. Those are my pieces. Check the formula, right? So I have 1, 2, 3, 4, 5, 6 carbons. I have 1, 2, 4, 6, 10 hydrogens. I have my oxygen and missing an oxygen. Okay, where does that oxygen show up? In there. It doesn't, not directly, right? You might see it. Well, you're definitely going to see a carbon attached to that oxygen, right? In the carbon NMR, and you might see a hydrogen attached to the carbon attached to that oxygen. Not, but you probably will. but you're never gonna see that directly. So this is where checking your formula will help keep you from going down the wrong path. Okay, make sense? That oxygen can't go where? Here, because that would also then be an estimate. Okay, so I'm not gonna do that. So we're gonna put that somewhere else. All right. How might we look to see where we're gonna put the oxygen? Is it gonna go on one of the methyls, is it gonna go on a CH2, or is it gonna go here? And it might go both, right? In two places, but we can at least try to figure out something. All right, so where's our electronegative atom region for our carbon? It's there at 70, okay, the triplet, 2H system, and then here at 4.3 or so, it's 2H system. So our CH2 is attached to the oxygen. You with me? It's in the electronegative atom region, electronegative atom region. Okay, so I'm gonna go ahead and do this. Okay, to get bigger pieces. Okay, so far so good. All right, now I want to try to make some of those smaller pieces into bigger pieces. And the way I will probably do this is try to find something easy that I can find. So I got either the quartet labeled here on this system, or I got my triplet on this 3H system. Okay, so that means if it's a triplet, it's next door to the CH2. If it's a quartet, it's next to the CH3. Those two pieces correlate to one another. Okay, so I can make this into that. Okay, now one open valency, one open valency, one open valency, three open valencies. Okay, so now it's a matter of just putting it on and seeing what are the possible arrangements and what makes sense. Okay, let's say I tried to put the aldehyde on this position, okay, right here. If I do that, okay, this hydrogen is attached to this carbon, and this is the carbon next door. What is this hydrogen peak going to appear at in terms of split? Doublet. Okay, so if I put that there, I need to have a doublet for the system, and I have a, so I automatically know I can't put the aldehyde on this carbon. Okay, with me? Okay, so in terms of connectivity, it has to go to this carbon. Okay, and right now, the difference between this is cis trans EZ, and I told you you're not responsible for cis trans EZ at this point in time. Okay, it's more advanced with Jade, obviously. We actually get this. So you put it in either one of these and be okay. There is a right answer between the two, but for our purposes, it's going to be good. Yeah. All right, with me so far. So we good. That piece is now with this piece. So we cross those out. Two open valencies. Two things. Okay. If I put my CH3 here, like that. Okay. Those hydrogens on this carbon. This is the carbon next door. This would appear as a doublet. Now we have a one CH3, and it is a. Oh, I have two CH3s. I have the CH3 that was triplet, and now I have the other CH3 that I'm trying to find, which is a. So can the CH3 go there? Nope. Okay. So that means my CH3 has to go here, and then that piece has to go here, and then we go and check what would this look like and verify that everything matches as we go through. CH3 in the normal region is a triplet, check, right? CH2 in the electronegative atom region as a quartet from being next door to the CH3, check. No hydrogens next door here, so that would be a 1H singlet in the proton NMR in the vinylic region. Okay, 1H singlet in the vinylic region. Okay. This methyl is going to be a singlet, 3H in the allylic alpha carbon region. So that's shift it up over here. Higher. So that checks. And then my aldehyde as a singlet in the aldehyde region. Yeah, go ahead.
Did you put your methyl group where your hydrogen is instead?
So do this?
Yes.
No, because then the hydrogen is next door to my aldehyde, and then that's going to appear as a doublet, and this one appears as a doublet. Okay, so I would have doublets for each of those. Now you could do cis and trans, right? So I could flip these, and that's okay. Because it doesn't matter whether this hydrogen is cis, it doesn't matter, but from what you're doing, it doesn't matter. Hydrogen is cis to the aldehyde or trans to the aldehyde, but you have to have these two groups attached to the carbon over on the one side, and then your aldehyde and your methyl attached to the carbon on the other side. And it could be vice versa, right? Because if I flip it 180, it's still the same. Okay, make sense to everyone? Questions on that one? You're right. All right. Numero trace. Tennis manual?
Oh, for two.
No. That would
Did you
be
get that right?
for you for real equipment. Okay.
This is what I had originally. That right there. But
All right, I told you the Caroline's 142. I don't know, probably the math spec that I have is nonsense, so I made it easy. I told it 142 multiplied out to get formula. So we get C8, 1402. You use then our 8 minus 14 halves, which is 7, plus 0 halves, plus 1. So we're at 2 units on saturation again, triple bond, 2 double bonds, double bond in a ring, or 2 rings. Okay, so what we're thinking, we go to our IR and try to find things as we go forward. Okay, so we look, looks like just clearly sp3, maybe some sp2, but definitely sp3. Carbon hydrogens, we have this big haunting peak at 1720, which is probably going to be then either an ketone or an ester, the higher numbers, right? Could be potentially an aldehyde, but then we have to go to our carbon NMR and see where that comes. This comes at 170, a little bit 168, which is more suggestive of what? Ester and acids at that region, and we don't have the big honking OH in our IR, right? So we know we don't have the carboxylic acid. So that, working that together is pretty indicative of the ester, okay? And then we have this peak here, which means carbon-carbon double bond. So it's similar to what we just did, but now it's an ester instead of an aldehyde that we're able to put together. Okay, so let's do this. There are 2 oxygens, and then we have some type of double bond. All right, so now we're going to have to figure out what type of double bond we have, and we can do this with carbon NMR and proton NMR. Make sure I got it right. Here. This is that's the right proton NMR, right? I'm getting lost in my paper. Okay, so we look at here, it says singlet, triplet for these two, because this singlet is our ester carbonyl, and then these two in the vinylic region are for a double bond. So that would mean a carbon with no hydrogens and then a carbon with 2 hydrogens. So it's a disubstituted, but it's a specific disubstituted. And I should see 2 hydrogens in my vinylic region for my proton and my. Okay? Make sense to you guys? Over here. Yeah. So our double bond, this is where the carbon NMR really comes in handy with the double bond arrangements. It's going to look like that. Okay, so far so good. Play my carbons off of my proton. Zooming back out. So we already did a little bit of this. No correlation on the ester, because there should not be the 2 hydrogens or the 2 hydrogens on that triplet. So there's 1 carbon, but those 2 hydrogens are non-equivalent, right? Because one is going to be on the face to one group, and then trans to the other group, and then those are going to be cis to that group, and then trans to the remaining group. So you get different peaks for that, which is fine. Then we got our triplet and our 2,8 system here, which is in our electronegative atom region. So I can already, since I only have 2 oxygens, I can go ahead and make this bigger to begin with if I want. I could write my CH2 and put it on there later, but that's the only thing that's going to come up there based on what I have. Okay, with me? Okay, so I have that. Then I have overlapping 3H and 1H, which is a CH3 and a CH, because I have the 3 peaks there. So 2 and 1 is 3. So I have the doublet, which is my CH. The big Q is the 2 equivalent methyl groups here. And it's bigger because there's 2 equivalent, giving rise to a larger peak. Right? And then my 3H is over here, even though it's on the end over here and over here, it's because the number of hydrogens can move those carbon peaks for you, right? So it's not just the chemical environment, it's also the impact of how many hydrogens on the peak as to where they come in that region, right? Yeah, makes sense? Remember we said methyls are usually around 10, a normal methyl, CH is normally around 20, CH is around 30, and the normal hydrogen is around 40. All right, so that's really going to shift you around. Okay, So this CH3 being over here tells you it's not normal. It's probably shifted from being close to something that's going to pull it over. Right? Okay, so far so good? Okay, did I write any of these pieces up? Probably not. Okay, so I said CH, CH3, and then 2 of these CH3s, which have to be equivalent wherever I put them. So they're going in a pair somewhere. Okay, so far so good? Okay, we can pick somewhere to start where life gets easy. Okay, this 6H, so those 2 equivalent ones, is a doublet. Yeah, the only way to get the doublet is being next door to how many hydrogens? 1. Do we have a 1 hydrogen signal somewhere? Yep. The only place we have a 1 hydrogen signal is here. And if we put both those methyl groups here, they would be equivalent. Correct? Okay, so that all makes sense to me. So let's go ahead and do that. Okay, 1 open valency, 1 open valency, 2 open valencies, 2 open valencies. So I still have some work to do to try to make some bigger pieces and figure out where things go. Okay, so what else can I go to? This 2H signal is next door to 1 hydrogen. I could go there. 3H singlet. Okay, so my methyl group has to be next door to no hydrogens. Let's try that and see if that helps me. So my remaining methyl group can't go here. That would have a molecule. Okay, if I go here, that carbon's next door, does not have any hydrogens, so that would work. If I go here, doesn't work. If I go here, that does work. Okay, so I have 2 options right now for the methyl, either here or at one of those positions. Okay, so I don't want to put it in the I just kind of think about my possibilities. Let's look at this one. All right, so this is next door to 1 hydrogen for my CH2. All right, this would not be next door to any hydrogens if I put it here. If I put it here, not next door to any hydrogens, if I put it here. Okay, so that tells me then that that CH2 group has to be attached. Does that make sense to you guys? Okay, so I'm going to put these 2 pieces together and make a bigger piece. So there's my CH with the 2 methyl groups. That piece is gone. That piece is now this piece. So I have my methyl with 1 open valency. I have this with 1 open valency, and I have this with 2 open valencies. So there's only one way to put it together, which is to take this and then attach this to one of those positions of my double bond and attach my methyl to the other position. Make sense? You see how I tried something and I didn't like it because it was too ambiguous, so I tried something else until I got something that was pretty conclusive. And then once I was happy, I put that in, and then I got my system. Now I'm going to check, and then I'll get your question back. Okay? Did I do something wrong? It's a lot of back and forth. It's really easy for me to make mistakes when we're going, so just catch me if I do. Okay, so we try to predict. Okay, these 2 hydrogens are going to be non-equivalent to one another, and they